Today we are going to do section 5.2, which is infinite series, which is on page 450. Now the infinite series is a bunch of stuff added up infinitely. You have an infinite list of stuff and you're going to add it all up and see what happens. Well, the first question, of course, is what does that mean? How do you add stuff infinitely? So first, let's give a definition of what that means. To add a bunch of stuff infinitely, we have the first thing we need to write down is something like this. Okay, well, from n equal to 1 to infinity, and you add a to the power n. That means, of course, you take a1 plus a2 and you keep adding unto infinity. But what does that mean exactly? How do you add stuff to infinity? We can't reach infinity. The definition of it, to be exact, goes like this. We will define something called a partial sum, sum k, okay, where we only add stuff up to k, n equal to 1 to k of a of n. So you add from a1 to a2 to a500 all the way up to ak, okay? So, which can be done, right? Because it's only finite. K might be a billion, but it's still finite. So you can add it all up. So we know what this means. Now, and then the next step is that we will watch what this partial sum does. The limit as the partial sum goes to infinity. K approaches infinity. Now, if this limit exists, then we will say that this summation exists and it converges and becomes some value of what this limit is. Okay, let's say equal to L. If A exists, then this sum exists and will go equal to L. That's how we define the infinite summation. Is we check to see if the partial sums exists as the k goes to infinity. So you add up more and more stuff together and see if it approaches a fixed value. Well, you say, well, let's say if an equal to 1, each one of them equal to 1, which means if you add them all up, they're going to go to infinity, right? In that case, we will say that the sum diverges or doesn't exist, or it goes to infinity. But if the partial sum does exist, the limit of the partial sum does exist, then we're going to call it, then the summation does exist. Now, why would you be able to eat a whole infinite amount of, why would you be able to add a whole infinite amount of stuff and while the result is finite? That is, that's not as hard as you might think. For example, let's consider the most classic example of an infinite sum that still add up to be finite is the sum of, how does your book put it? Okay, let's add this. Okay, let's see the sum of, at the bottom of the page, from n equals 1 to infinity of 1/2, okay, to the power n minus 1. Now that, if you write this sum out, starting at n equal to 1, that would be like 1 plus 1/2. We're not going to start at 1. We're going to start at 1/2, because who cares about 1? Huh? Let's start at 1/2, okay? And so this sum is 1/2, right, plus 1/4 and plus 1/8. You keep dividing by 2 each time, and you keep adding unto infinity. Now this sum converges, or at the least, it doesn't add to infinity. And how do I know that? You can know that intuitively. Let's say you have a cake that you're eating. Here's your round cake, okay? And then the first time every minute you eat a certain part of it. And here's the rule. Each minute, you're going to eat half of what's left. So the first minute, you eat half the cake, okay? That's the 1/2. You ate that much. The second minute, you eat what's half of what's left. So you eat this much, okay? The second minute. The third minute, you eat half of what's left. And you keep doing that, right? See, that's the third minute. So after 3 minutes, you ate that much. But theoretically, you can what the rule is, you will cut each minute, you cut the remaining cake in half and then eat it, right? If you keep doing that, theoretically, you can never finish the cake. That is, you will never eat more than one cake, right? Of course, in time, it will be very difficult for you to cut anything because it's too small to cut. But theoretically, you can go on forever. Every minute you eat half of what's left over. So you continue to gain, but you've never even reached the entire cake. So that's how an infinite adding infinitely can actually be finite. See, that is a very a classic example of the cake eating trick. So that's how stuff that you can add an infinite amount of stuff, but the total amount is still finite. In fact, you never even finish the cake, right? Because each minute as you go on, you're only eating half of what's left. So there's always something left. All right. So now that we have done that, let's look at the next things. Let's look at the definition. So the definition on a couple pages later, an infinite series is defined as the partial sum. You add up a finite number of them and see if all the partial sums go to a fixed limit. If it does, then the infinite series exists, and if it doesn't, then the infinite series doesn't exist, and it's called divergence. Okay, diverge means it's going nowhere. I mean, it might go to infinity, might bounce around, who knows. But anyway, so this thing just diverges if the partial sum limit doesn't exist. Now, the one small note I should mention is that when you have the infinite series can be written in different ways, but it's the same infinite series. For example, towards the middle of the page, I'm on page 462, where you have two infinite series. For example, you might have an infinite series written like this: n equal to 2 to infinity. Now notice n doesn't have to start at 1 or 0 or anything. It can start anywhere. It's your series. You name it however. You start it wherever you want. However, because of that, sometimes two identical series might look different because of the way you write it. Consider, for example, these two series, m equal to 1 to infinity, and that's 1 over m plus 1 squared. Now, if you consider these two series, you notice they're identical, actually, especially if you write them out. See, the first term, n equals to 2, that's 1 over 4. The first term, m equal to 1, but 1 plus 1 is 2, then it's 4, and so on. You see, I mean, they're turn by turn identical. So they are the same infinite series, but it's written, but just there's a slight difference in notation because your counting system is slightly different. That's all. So so that's that. Now let's look at example 5.7 part A. Example 5, we have a bunch of stuff to be added up, and the question is, does this add up to be anything, or does the series diverge, which means it goes to infinity? Now, as you can see, each term is in the form of n over n plus 1, right? And the thing about n over n plus 1 is that it's give me a second here, let me get my note. Now, what happens with this series? Well, being that n is big, so if we have n is bigger than 1, okay, for n is bigger than or equal to 1, you can see that we can work from there to add n to each side. Then we have 2n is bigger than or equal to n plus 1. And then if we divide everything by n plus 1, then we have n over n plus 1 is bigger than equal to 1 over 2. See, rearrange the numbers here, divide by n plus 1, divide by 2, so we get that. Which means each one of these terms are going to be bigger than half, which means the summation as n goes from 1 to infinity of this term is going to be bigger than or equal to summation of 1/2. That is, you have a bunch of 1/2s added, keep going, okay, all the way to infinity. That, of course, diverges. This goes to infinity, so it diverges, and therefore this sum diverges. Now, your book gives an answer where it says, oh, you see a pattern here, right? The book came up with, I don't know, the first 4 partial sums and says, oh, take a look at the pattern. That is not acceptable proof. I do not like to say that the book is wrong, but that is something like if we see the first 4 patterns of a series, I mean the sequence of partial sums, that's fine as long as if we're guessing at what the answer might be. We still need to prove it. You see, this proves, so for all n, okay, every single n, this relationship is true. See, you have to prove all of them, not just the first 4, because just because the rule applies for the first 4 terms doesn't necessarily mean it's going to go on forever. Therefore, the summation here, this is the complete proof actually is that this thing will diverge, okay, conclusively, not just because the first 4 items, because we don't care what the first 4 items or first 4 billion items do. The question is, what would the last do? And can you have to prove that the first 4 items behavior is identical to all the rest of it unto infinity in order to for your proof to be truly complete. Yeah, something like this. You see the first 4 items that was used. That's good enough for like the 5th grade aptitude test or something. And you know, you look for the pattern. It's not acceptable for calculus 2. Okay, that is just, yeah, it's just not a thing. Okay, so having said that, let's look at part B. Part B is much simpler. Okay, that is -1 to the power n. We know that it becomes a -1 if n is, I don't know, odd, evens. If it's even, it becomes +1. If it's odd, it becomes -1. So we can prove that this thing is gonna flip back and forth forever unto infinity, and therefore it diverges. Next, part C is another partial sum. Okay, and again, your book says, well, let's look at the first 5 terms, and if it does if it looks like it has a pattern, that proves that it does this. No, it doesn't. That's not enough proof. And so to actually prove it, I have it written down here. Now, if looking at the first, I don't know, 5 terms of and detect a pattern isn't good enough to prove that this thing goes diverge or converge or whatever, how are we going to do it then? You have to prove everything for every single n. Okay, so the way we prove it in this particular case is we're going to break this thing up with a partial fractions calculator. And that equals to, this happened to be equal to a fairly simple relationship of 1 over n minus 1 over n plus 1. Now, if you write this thing out, we will talk about this type of series later. It's called telescopic. The telescopic series has a very interesting situation. If you write it out, you will see it. For example, if we were to write this out, then the partial sum, say going up to k, which is the sum adding up from n equal to 1 to k of that thing, right? It will equal to a very interesting situation, which is we'll have 1 minus 1/2, okay? And then what's the next term? The next term, n bumps up to 2, so then we have 1/2 minus 1/3. And you keep doing that, and then minus 1/3 plus 1/4, and so on, all the way to something. So eventually you get to k is eventually you get to something like 1 over k. Okay, on the kth term, 1k minus 1 over k k plus 1. So as you notice, each term disappears. Okay, we can prove that for each n, because n bumps up 1 at a time, so each term gets killed. So all you have left at the s of k, you can write down s of k exactly as the first term, 1, and the last term that didn't get canceled out. The first part always get canceled out. So 1 over k plus 1 is what the partial sum is. Okay, here's the partial sum. End up being. Now, knowing that, then as k goes to infinity, if your k goes to infinity, then s of k then approaches 1, because that dies out because k is approaching infinity. So s of k approaches 1, and which is why this is a convergence series, and not just that it converges, we know exactly what it converges to. So that is that is a more complete proof instead of what your book said is, oh, we'll look at the first, 5 terms or four terms? Yeah, I only looked at 4 terms this time and figure, that looks, no, 5 terms. I'm looking at the wrong thing. Okay, the first 5 terms is good enough for anybody. No, it's not. All right, you have to prove that the entire thing, for all n, this pattern follows. So, and this is called the telescopic series, and we'll look at it a little bit later. A few moments later, we'll talk about it. The book will talk about it again, and then admit that this is a telescopic series and should have been done this way. So why do they do it this way? Here, I have no idea. Yeah, because that is a bad habit to say that the first 5 items in the series look a certain way, and therefore it must look that way forever. That's an incomplete logic, okay, which is not acceptable in math. All right, so having criticized the book, let me erase the board and we'll keep going. Next, let's look at the harmonic series. The harmonic series means something like this. You add up a bunch of fractions in order. That is called 1 over n, which means that you add 1, n equal to 1, 1/2, 1/3, etc. Now, where does this thing go? Does it converge or diverge? The harmonic series, if we were to calculate it, you notice that it is gaining, but it's gaining slowly. As your book has at the bottom of the page, where you see even if you go up to 1,000,000 terms, it only grow up to be about 14 or so. So it's very slow. So according to this pattern, you might guess that, oh, it must converge. No, it does not, which is why I said earlier, just the first few terms doesn't tell you anything. Okay, it might look like it's dying, but it's not. Even if you look at the first 1,000,000 terms, only make it to 14. How far can it go? Well, it can actually go to infinity. I mean, as slow as it's going, and plus it's going a whole lot slower afterwards too. But even then, as slow as it is, it still make it to eventually approach infinity. Despite its incredible slowness. Now, the proof that the harmonic series diverges is as a cute little thing that goes like this. We have, let's look at the next page. So let's look at the partial sum. Now the partial sum is actually, we don't even care about the partial sum that much. Let's just write this out. When you add this up, you compare the harmonic series to something that looks like this. Let's say we have, this is bigger than or equal to a different series, okay, that converges. And what might that be? So we'll design a different series that's smaller than the harmonic series that still diverge. If that still goes to infinity. If we can find such a series, then of course the harmonic series is forced to go to infinity. So what we're gonna do is see these two things. We're gonna find something smaller than it. Okay, 1/4. Which is slightly smaller than that, right? So that's the first part that's taken care of. And then, let's see, plus 1/2, no, sorry, this is 1, okay, and then 1/4 plus 1/4. So we go all the way, this is 1/4, we line it up with the 2 to the power n. That is, there's 2 and there's 4, and anything before 4 but more than 2, then we line it up with 4. And this pattern continues, okay? There's 5, 6, 7, 8, and now at the next point it becomes 2 to the 3rd power is 8, and we line all that up be 8. See, what you're doing here is that plus. So there is, so you're lining up with numbers that's smaller. 1/8 is less than 1/5, and so on. And furthermore, so you continue doing this, and so each time you reach 2 to the power n, so the next one will be 16, and we'll write out a whole bunch more, right? And so as a whole, this particular thing is smaller than it. However, each pack of here is equal to 1/2. So each time there's more and more added together, but they always equal to 1/2. And therefore, so this series is called, I'll write it over here. This is This series is basically what you're doing is the sum of 1 plus something. What is this? Is 2 to the power n. Well, actually, we don't care what it's called. The point is that's what we're going to do. Okay? Yeah, you can give it a name and figure out exactly how the n cooperates, but we don't really care. So the point is this is going to be equal to the sum of 1 plus 1/2, and you keep adding 1/2s, even though you're gonna require more and more terms to add up all those 1/2s, but that's okay because you got an infinite amount of stuff in front of you, right? So you can always round up another 1/2, even though it will take you longer and longer to collect enough 1/2s. And being that this is a collection of 1/2s, then the game is over. Okay, this goes to infinity, and therefore the harmonic series also go to infinity. Now notice that I did not say that this is a pattern based on first few items. I'm saying that this pattern go on forever, okay, for all n, and which is why this proof is valid, and that is not incomplete like some of the other stuff that your book wants to do. So then, okay, so now we proved the harmonic series diverges. Next, let's look at theorem 5.7, which is a bunch of rules about the summation series that you already know, such as you can split up the summation symbol to be addition or subtraction, or multiply by a constant, as we have already covered that, but this is just a repeat to make sure you know this. All right, so knowing that, then the next thing we do is look at example 5.8, where you apply some of the summation rules, which is straightforward, so I will leave that as homework. Next, let's look at the geometric series, which is a series in this form. Now, as you can see, a is just some constant, so a can be taken out if necessary. And that is just written that way, so it's more convenient to look at. Now, what happens with the geometric series? Well, let's see.